Hi, welcome everyone to the meetup of the San Diego chapter of Paper 3 Love. The presenter this evening is Mike Mull, and he's going to be presenting a paper by Cynthia Dwork from 2006 called Differential Privacy. Let's have a warm welcome for Mike Mull.
Thank you. Can you hear me and see me and all that kind of good stuff? Okay. So yeah, the paper is called Differential Privacy, and the topic is differential privacy, so that's convenient. Cynthia Dwork is currently a researcher at Microsoft. She's both a luminary in this field of privacy, but also is credited with inventing the concept of proof of work, if any of you are cryptocurrency hackers like me. So she's done some pretty impressive stuff. This paper was also filed as a patent at Microsoft around the same time that the academic paper was written. So here's the basic problem that this is addressing. It's privacy in what are called statistical databases. So what that means is databases where the people using them are trying to compute statistics on the data, you know, counts, sums, averages, means, and sometimes more complicated things than that. So this isn't a database where you can look up, you know, somebody's salary. It's meant to be data that you can do analysis on and find trends and you know, other statistical information, but as the name would suggest. So there's a variety of reasons why I think this paper is interesting. First and foremost, I think, is because it's not, at least to me, obvious that if you take data and you anonymize it and take out personally identifiable information, that you still have a privacy issue. You know, in fact, I did this in the past where we released data sets to people to study, and you know, the lawyers said just take out the names and addresses and you're fine, and we assumed that was correct. It's also one of the only privacy methods that does not use any form of cryptography directly. There's some arguments from cryptography leading up to the ideas, but it doesn't do encryption. It doesn't do, there's no zero knowledge proof type stuff in here that you might have seen in other contexts. There's a lot of practical uses for this, and in fact, it's used by a lot of companies currently. You know, the Google, Apple, Facebook all use this in some way or another, or in some cases misuse it. It's reached a point now where it's mature enough that people are applying the ideas in this to other computer science research problems, which I think is, you know, the sign of a really interesting idea. It's also a topical thing. A couple weeks ago, there was a Senate hearing about data privacy, and people talked about differential privacy. There was an article in Wired, I think, a month ago about how Apple's not doing it right and thereby leaking people's privacy. So, you know, it's one of those things that you'll actually see in the news, even though it's a fairly deep computer science concept. So basically, I'm going to run through the paper in kind of the way that it's structured. Just introduce the ideas a little bit, go through what they call the impossibility proof, very informally. I'm not going to try to do any of the math. Then I'm going to try to cover the formal definition of differential privacy and discuss methods how they achieve that. That's pretty much the fourth and fifth section of the paper. So the things I think I'd like people to learn from this are privacy is not guaranteed by just de-anonymizing data. Understand that this method is a randomized method by nature. So when you're asking questions of these statistical databases, this method doesn't give you the same answer on subsequent queries, even if it's the same query. There's randomness involved. Also, that there's trade-offs between the randomness added and the amount of accuracy you can get. So you want to maintain privacy, but maintaining privacy, you know, to the extent that you want, may involve adding enough noise that the answers get further and further from the true answers. And so you can't just simply, tighten the privacy as much as you want, because the more private you make it, the less precise the answers become. I'm also going to talk about how the privacy mechanisms can be composed, and what happens when multiple queries are made on the database, or multiple people make queries on the database. And finally, I'm going to try not to talk at all about hash functions. This is my this is my third Papers We Love presentation, and my first two were about min-hash and hyperloglog, which is pretty much all hash functions all the way through. So I'm going to try not to talk about them. So privacy in the context of these statistical databases, the first really formal attempt to define what that meant was done in 1977 by this researcher named Dalenius, Swedish, I believe. And he said that what we desire is access to the database should not allow you to learn anything about an individual that you couldn't learn without access to the database. So for statistical databases, that's sort of the ideal scenario. In the paper, what they essentially say is you can't do that. There's circumstances beyond the control of the people doing the study that make that impossible. And so what they propose, what Dwork and Frank Masheri and certain other people propose, is this idea of differential privacy. And the sort of fundamental idea of differential privacy is that your presence in, your participation in the database should not make any difference to your risks, your privacy risks. So if you participate in a study, a medical study, it shouldn't affect your chances of getting health insurance. That doesn't mean that there's not some other piece of information that people could use to piece together something about the data that's in there. But if merely participating in the study is not going to expose you to risk. So it's a slightly lower barrier than what Dalenius had wanted, but it's achievable. So unfortunately Nate's not here tonight. We talked about semantic security last month too. The idea that Dalenius introduced is very similar to what people in the security field call semantic security. This was an idea that came about in the early 80s, which was about 4 or 5 years after Dalenius published his paper. And there were two security researchers who came up with this idea, and these are two kind of informal statements of it. And oh, thank you. I got some down here, but I'll take some more. So the informal statement of the idea is basically that the ciphertext that you receive should not tell you anything about the plain text that you didn't already know. The more formal version of it goes into the classes of algorithms that you can apply and that sort of thing. But basically the idea is that you can't compute anything from the plain text given the ciphertext that you couldn't have otherwise. And the reason I introduced this, even though it's not covered heavily in the paper, is that the impossibility proof that they go through relies essentially on this idea, and a sort of alternative statement of this idea. So what they essentially show is that the privacy, the types of privacy that Dalenius wanted is not achievable for the same reason, for reasons along the same lines of why they use the same arguments that people use to show that semantic security is achievable. So just I want to run through some informal reasons why this is impossible, because they do discuss it in the paper as well. Who knows who Terry Gross is and who doesn't?
The NPR.
Right. I have no idea why she's used in this paper, but there's this sort of famous example now in the paper. Terry Gross is an interviewer on a show on NPR called Fresh Air. She's been doing it for 30 years, and listen to it, because she's a really good interviewer and she does a lot of interesting interviews. But for some reason, they used her as an example of a privacy breach in this paper. It's not a particularly serious privacy breach, but the situation is this, that somebody's put together a statistical database, and one of the facts in that statistical database is that is the average height of Lithuanian women. So if you happen to know that Terry Gross is 2 inches shorter than the average Lithuanian woman, then by extension you know how tall Terry Gross is. If your height were a secret that you did not want to share with people, that would be considered a privacy breach. And this illustrates the idea that they're trying to get to, which is that even though the database may be anonymized and say nothing about an individual, if somebody has access to this auxiliary information, they can still get a privacy breach. And the information doesn't even have to be in the original database. And the essence of their proof is basically showing this formally. And again, contrasting that with semantic security, if you have so-called auxiliary information about the ciphertext, semantic security says that shouldn't help you to decrypt it. So even if somebody says the message is either cat or dog, that does not aid you in determining which of the two it was from the ciphertext. Okay. So I need to set up a bunch of preliminaries for this proof part. One is what they refer to as interactive and the non-interactive situation. So the interactive database is there's some sort of database manager or privacy manager that sits in front of the database, takes in the query, may be able to do some analysis on that, and then returns you the data based on what it sees in that query. The other scenario is the non-interactive, where this is probably much more common, and many of you have probably dealt with data like this in your work, where you have some data and you want to release it to somebody, and so you just take out people's names, or you take out their addresses, or reduce the zip code to 3 digits, or just give the county or something like that. That turns out to actually be harder to deal with from a privacy perspective, because you can't know beforehand what sort of questions people are going to ask. So you don't get to see the queries that are made on the data before you give the data to the end user. And just quickly, these are not covered in the paper, but I wanted to point out that there are actual privacy breaches. This is not a purely theoretical concept. Probably the most common type, and the type that has gotten the most press, is what's called a linkage attack. There's several examples of this, but the two that I find interesting and that were pretty prominent. One was, I think this was in the 90s, a state on the east, I think maybe Massachusetts, released some anonymized medical data. And when they put it out, they said, "Don't worry about this. We've taken out all the private, personal information. Nobody's going to know anything." Lo and behold, a privacy researcher, who I think at the time was a graduate student named Latanya Sweeney, said, "I dispute that claim." And she took that data and managed to match it up to voter record data in the same state and actually de-anonymize people. She didn't reveal their data, but she showed that she was able to identify individuals in that database of de-anonymized medical data. Latanya Sweeney is still a very prominent researcher in this field also, and she's the inventor of a technique called K-anonymization that they mention in the paper also. Another big one that I dealt directly with was the Netflix challenge. Is anybody here old enough to remember that still? Okay, so I think 2006-ish, Netflix decided that they wanted to improve their movie recommendation algorithm, and so they took their entire set of data where people had given stars or ratings to movies and released it to the public. But in the process, they took out anything that would identify individuals. And subsequently, people took that data and matched it up with ratings that people had made on IMDb, and manage to de-anonymize certain people in that database. I happened to be doing recommendation stuff at that time, so it was kind of a big deal in my world at the time. Another type of attack that people can actually accomplish is something called a differencing attack, and there's been some high-profile cases of this too. There was one case where they did a national cancer study, and it turned out that there was no personal information, but there was information on the county that people lived in and their race. And it turned out there was one African-American woman in a county in somewhere in the South who had cancer. And so people were able to say, show me all the people in this county who have cancer, or give me the count of all the people in this county who have cancer. And then they could say, okay, give me the count of all the people in this county who have cancer who are white. And the count was one different. Ergo, that lady was one of the people who had the condition. So, and reconstruction attacks are kind of an advanced version of that. I won't explain them too much, but reconstruction attacks are really tricky and pretty devastating in that given enough statistical information, you can actually reconstruct the original source data. Okay, to the actual impossibility proof. So the semantic security perspective says that an adversary that receives the ciphertext has no advantage over an adversary simulator that receives nothing. I'm going to go into this a little bit more because this is a kind of a strange idea. And what they show in this proof is essentially that an adversary simulator, an adversary which gets the return data from the database versus an adversary simulator that only gets the auxiliary information, the adversary actually has an arbitrarily large advantage. So it does not have the properties of semantic security. So this idea of an adversary simulator is kind of weird. And I think if you are a security researcher, it probably looks pretty familiar. But if you're not a security researcher, it probably is bizarre. So I extracted this line from a paper on this technique, just to prove that even to people who work in security, it's a little bit strange. Because they literally say this is very strange. So in any case, the idea is you have an adversary and you have an adversary simulator. The adversary gets what will later be called the utility vector from the privacy mechanism. The adversary simulator does not. They only get, both parties get the so-called auxiliary information, but the simulator does not get the data through the privacy mechanism. And so what they show is that the simulator can't really do anything, whereas the adversary can, and in fact has an arbitrarily large advantage over the simulator. And so that's the crux of the proof, and I know it's a weird concept, but if you can buy that idea, then the proof makes a little bit more sense. So there's these various pieces that they discuss that go into the proof, and I'll have a picture of these too and how they fit together. But there's the actual database, which they say is drawn from a distribution of databases. There's the mechanism, they call it a Turing machine, but it's just a function or procedure that takes the data and does something to it to make it private. The so-called utility vector, which is the data that's returned from a query through the privacy mechanism. There's a thing called a privacy breach decider, which again they describe as a Turing machine, but just think function or procedure. The auxiliary information generator, which is something which does have access to the data, to the full database, not just the privacy mechanism, and so can presumably should be able to find a privacy breach in the database if one exists. And then there's the adversary and the adversary simulator. And the way these basically fit together is that the auxiliary information generator gets, as I said, gets the database and knows about the privacy mechanism. The adversary only gets the the data through the privacy mechanism via this thing called the utility vector. And the adversary simulator only gets the data from the auxiliary information generator, not the data from the database. And then both the adversary and the adversary simulator can try to find a privacy breach and ask the privacy breach decider, hey, is this a privacy breach? And it will say yes or no. So I realize this is a lot to absorb, but so the utility vector, as I said, is basically the data that's returned to you through the privacy mechanism. And this is analogous in encryption to the actual ciphertext. And the point they basically make is that the difference between this and ciphertext of an encryption scheme is this has to have some utility to the person that receives it. You know, so if you're an eavesdropper and you get the ciphertext, it doesn't have to have any utility for you, and you would, in fact, people would hope that it doesn't. But there's really no difference here between the adversary and the end user, and so this thing that's returned from through the privacy mechanism has to have utility to the person that receives it. So more preliminaries. So they also make some fairly reasonable assumptions about the situation for starting on the proof. One of them is that any database that's taken from this database distribution does have a privacy breach. If it didn't have a privacy breach, then just give people the whole database, because there's really nothing to reveal there. Marvin and I had a discussion about what sort of database that might constitute, and the only thing I could think of was like genomic data for a fruit fly or something. I decided not to use a picture of a fruit fly though. So. The other assumption is that the utility vector has enough entropy that you can extract a random uniform value from it. Is everybody fairly comfortable with the idea of entropy in an information theory sense? Okay. So basically, we need to take that utility vector and get from it an L-bit uniformly distributed random value. And this is done with a thing which you'll have to take my word for it because it involves hash functions. But there's a thing called a strong random extractor that will do this, and it's you know, a fairly well-established algorithm. And then the third assumption is that the chance of an arbitrary procedure finding a privacy breach without the auxiliary information is fairly low. So, you know, a quick example of that, if we go back to that medical database situation that we talked about earlier, if you didn't have the voter data, it should be relatively hard to find a privacy breach if you didn't have the voter data as auxiliary information to match up people's identity. So this is just basically a non-triviality condition which says that it's not easy to guess a privacy breach without the auxiliary information. Okay, so then in the proof they go through two scenarios. One they call the simpler case, and in this case both the auxiliary information generator and the adversary are getting the same utility vector. So the way they put it is that they learn the whole thing, but essentially what they're saying is the utility vector W, it's both parties are getting the same thing. That makes it easier because they're remember how we're saying they're extracting this random value. They extract the random value so they can use it as a key to encrypt the privacy breach. And since they're both receiving the same utility vector, they can both get the same key, and that way it's easy for the auxiliary information generator to pass the privacy breach secretly to the adversary so that the adversary can figure out the privacy breach, but nobody else could. So yes, this is an incredibly contrived situation, but it does in fact show what they are trying to demonstrate. Does everybody know what a one-time pad is? Does anybody not know what a one-time pad is and want an explanation? Okay. for the purposes of this discussion, it's basically an encryption key which has the same length as the thing you're trying to encrypt. The name comes from, I believe, comes from encryption in like the spy world back in like the World War II, where they would literally have a pad with a mapping on it that they could use to encode a message, and somebody else back at headquarters would have that same pad, and they would know they were going to use that pad for that day, and they would use it, encrypt that message, and then tear that off and throw it away. So it was one time. I'm pretty sure that story's correct, but if it's apocryphal, I apologize. Okay, so the hard case is basically the same thing, except here, remember that we're dealing with random algorithms. So in the real case, the auxiliary information generator and the the adversary are not getting exactly the same utility vector. They're getting data which is close, but not exactly the same. And so they go through the same process here, but instead of using the strong randomness extractor, they use something called a fuzzy extractor. This idea of a fuzzy extractor was, as I'm told, developed for biometrics. So like if you get into your phone with your thumbprint or your face or something like that, the bits that your phone gets from your thumbprint are not always going to be identical, but they're going to be similar. And so this idea of a fuzzy extractor is basically something that will take bits that are pretty close and eventually give you the same key. And really the only difference in the proof when using this fuzzy extractor is that the utility vector has to have even more entropy in it for the proof to work, and they go into that in some detail. These fuzzy extractors are fairly complicated, but what they do is not too hard. There's one procedure that takes a value and spits out two random values R and P. And then you can pass on P being sort of public. You can pass on the P value to other people. And there's another procedure which, given that public value and another value which is close to the original W, is able to extract the same R. So again, they're able to, both the adversary and the auxiliary information generator are eventually able to get the same key from data that's not identical but is similar. I mean, if these two utility vectors were completely different, then that would be hopeless, but they're sort of guaranteed to be within a certain Hamming distance of each other, if that's a term you know. This is not appropriate. This is not anything to do with the paper, but just as a funny aside, when I first Googled the topic of fuzzy extractors, I got an advertisement for a vacuum cleaner. So, okay, finally, differential privacy. So this is the one equation on my slides, and this is the formal definition of differential privacy. So it's a relatively simple, but still takes a little bit of reflection to figure out. Basically, what it's trying to say is you've got these two databases, D1 and D2, and they only differ in one element. And so what differential privacy is trying to guarantee is that the privacy, the probability that you get the result S from D1 is more or less the same as the probability that you get that result from D2. So the hope being that you can't you can't query D1 and get one result and then query D2 and get another result and say, this is obviously D1 because this value couldn't occur in D2. For me, at least, a good way to think of this is to imagine that there's no privacy mechanism. So you're just asking a database for counts, let's say. And the example I sort of contrived for myself was, imagine you have a database, a medical database for individuals, and there's a field in there that says, that specifies what type 2 diabetes drug you take. For most people, it'll be none. But for a lot of people, especially in this day and age, there'll be something in that field. This occurred to me because both my father and my sister take metformin, but and that's not a privacy breach, by the way. Everybody knows that. So if there were no privacy mechanism, and there was somebody in D2 that is extra that's not in D1, and you say, show me all the people who take a type 2 drug in one in one data set it's going to be n, and the other data set it's going to be n plus 1 every time. So it's fairly easy to distinguish those two data sets just by knowing that particular thing about the data. So this parameter epsilon that you saw on the previous slide is sort of the key thing in differential privacy. In fact, you'll see this reference all the time to what's called epsilon differential privacy. So the epsilon is the value that you sort of control. It's the knob that you can dial. But the thing there is that, again, as I said before, if you make it smaller, that makes it more private, but you also have to add more noise to do that, which means the answers get further and further from the real answer. The log, I should have probably written this equation out too, but if you take the ratio of the probability in D1 and the probability of D2, and then you take the log of them, the log of that whole thing, you get something that they call the privacy loss, or the leakage, and it basically measures the amount of privacy you're giving away using that particular, those particular data sets and privacy mechanisms. I also noted here that this exponentiation of epsilon for small values of epsilon is very close to 1 plus epsilon when epsilon is small. And I have a picture of that just to verify it. So when epsilon is less than 1, exponent epsilon is basically almost the same as 1 plus epsilon. So it's kind of easy to see in that particular range the relationship between the probability on D1, the probability on D2, because that factor is pretty small. So those two probabilities should be about the same. But as you get into larger values of epsilon, the possibility for the probabilities on the two sides of that equation to vary becomes larger and larger. And this is what Apple has recently been accused of not paying attention to. They use values of epsilon that are too large, and so are sacrificing people's privacy. So,
Mike, can you go back for a second?
Yeah.
I had a question. Can you explain just a little bit more about what the differences between the two queries against the two databases are? What are we trying to protect there? What's the difference between the query to one and the query to the other?
Well, imagine the way I envision is you're doing the same query on both databases. And then you have this privacy mechanism which takes that query and returns you some data. So the hope is that it should be very difficult to distinguish the results you get from the first database and the second database. So if you run a query against the two databases, if you run the same query against both databases and you get substantially different answers, that's going to help you identify which of the two databases you're actually dealing with.
Right. So there would be one individual who was not present in database 1, but was present in database 2. And if you can tell the difference between the answers,
yeah,
then you can tell that the person who has participated in that other database, you've identified them and their privacy's been breached. Is that accurate?
You started to identify them, yeah.
With some level of confidence.
I think this next topic may actually help on it a little bit, so I'll, if it doesn't, point it out to me. But there's this concept they introduced called sensitivity. They specifically call it L1 sensitivity because of the particular sort of distance metric they're using between the two databases. But the basic idea is that a query function, a function that you apply to this data, the biggest possible difference that it could have between D1 and D2, in other words, these two databases that only differ in one record, is the sensitivity of that function. The easiest case to understand, again, is counts. So if you have one more participant in one database that you don't have in the other database, the largest difference that a count query could give is 1. It may give 0, but it could give a difference of 1, because the individual in the extra individual in the other database may match the predicate that you're searching on, and so we'll increase the count by 1. So that regardless of the size of the database, if you've only got a difference of 1 record, the sensitivity of a count query is 1. And that's a pretty easy situation to analyze. It's a little bit more difficult with other statistics because you don't necessarily know what the differences in magnitudes are. There's some tricks that people play in this field to sort of get around having to scan through the whole database every time, but roughly speaking, you have to figure out before you reveal the answer to people how much noise you have to add to mask the existence of that extra person. Does that help at all, Marvin, with your question? Okay.
I mean, does everybody else get what we're trying to? The idea of differential privacy relates to protection of one individual, whether or not the one individual participates in the database or not. That's part of the definition. So this is measuring that.
I apologize to people who are not SQL proficient, but I figured that was probably the closest I could get to an understandable sort of query that, everybody, it's relatively readable, I think, even if you've never encountered SQL. So the next question is, okay, I need to add noise to mask the existence of one user in the database that's not in the other database. And so the question is, what sort of noise do I add? This line that's straight from the paper says they add scaled symmetric exponential distribution with variance sigma. I have no idea why they put it that way. In every other reference on differential privacy, this is just called Laplacian noise, and they're the same thing. So I'm not sure why they use this term, scaled symmetrical exponential. And just this is what Laplacian noise looks like for 3 different values of the variance. So the sort of narrow pointy blue one is relatively low variance. And the orange one is sort of an intermediate value. And then the green one is a very high variance Laplacian noise. And you can see that when the mechanism picks a random value from these distributions. So every time you ask a query, it's going to pick a different point from this distribution. So even if you ask the identical query, you're not going to get the same value back. But you can see that depending on the variance, the value that you get back may be relatively close to the true value, or it may be, in the case of this green line here, you could reasonably get values that are, plus or minus 10 of your true value. So that's what Laplacian noise more or less looks like. And then the final thing is how much noise, how much of that Laplacian noise do you want to add to actually achieve epsilon differential privacy? And I debated whether to go through the proof, because it's not super hard, but I didn't want to have any more equations. So I'm just going to hope that you can accept that they accomplish the proof. And what they come up with is that to achieve what you want, the epsilon has to be delta F, which is the sensitivity over the variance of the particular Laplacian distribution that you're looking at. So another way to think of that is if you choose an epsilon of 0.1, then, and you know that the sensitivity is 1, then that gives you your variance for the distribution that you want to draw from. So, you know, as an example, if in the case of count queries, the delta F is 1. So you want if you want to achieve epsilon differential privacy, then for a count query you use a sigma of 1 over epsilon, if that makes sense. So so what I'm trying to do here is show what this really looks like. So these are basically draws from of Laplacian noise. So remember earlier I said you might have a database of where the count is 1 different. So suppose that in one database the count is 10, and the other database it's 11. And so you want to add noise to the result, so that somebody querying those databases can't tell whether they're getting 11 or 10. So if you in this case, this is like I think 10,000 random draws from a Laplacian distribution centered at 10. One's at 10 and one's at 11. But the epsilon in this case is 0.1. So you can see that these two distributions pretty much overlap. So if you were to pick 2 random points from the orange one and one from the orange one and one from the blue one, you really couldn't tell which of the 2 data sets it came from. The downside is that if you look at the x-axis, you'll see that you could also plausibly get, you know, negative values for the counts. The middle one is for an epsilon of 1, and again, if you were only picking 1 point from each of those histograms, there's a pretty good chance you couldn't tell which one it came from. But if you did have enough, if you were allowed to make enough queries to that database, you could eventually see that there is a slight difference between the mean of those 2 things. And then finally, the last one is with an epsilon of 10, and you can see that there, if you were to pick a random point from the blue histogram and a random point from the orange histogram, you could pretty easily tell which database it came from. And so you've got, you know, you've got a low variance here. You know, the answers are going to be pretty close to true, but you don't have a lot of privacy. Does that make sense to everyone? I was kind of hoping these pictures would give sort of a practical sense of what's happening in a simple case. So we're getting close to the end here. And, there's a brief section right after this where you talk about histogram queries, and I wanted to throw it in, even though they don't elaborate too much. I wanted to throw it in because I think it illustrates a couple of interesting points. I think the point they were trying to make is that you can look at histograms naively as being, if there are k bins in your histogram, you can look at that naively as being k queries, k count queries. So if you stop there, you would think that you would have to add noise. I think it's oh shoot, I think it's k epsilon over k, or k over epsilon. Do I see on the slide?
You do.
Okay. Okay. So the point they try to make is that when you only have one record different, the histogram is only going to change in one bin, so you can go sort of back to the situation where you are doing the 1 over epsilon privacy. But they sort of gloss over a point here, which is that they make the point that if you do k queries, you have to add more noise, because the cumulative effect of doing these queries is to give people more information about the you know, the noise that you're adding. And so to make the you know, if people are going to be making successive queries on the same data, you actually have to add you have to add more noise and limit the number of queries they can make, and I'll talk about that a little more. This idea is called composition. And so the way that it's sometimes used is in terms of you have one privacy mechanism and then you have another privacy mechanism and you apply them successively. That's one type of composition. And what happens is that if you have an epsilon1 differentially private mechanism and an epsilon2 differentially private mechanism and you compose them, then you end up with an epsilon1 plus epsilon2 differentially private mechanism. So less private, basically. And so what happens in practical systems that do this is that you have to have what they call a privacy budget, which means that you start off with some value of epsilon that's your budget for making queries, and after you've made a certain number of queries, you have to stop. This also applies, like another issue that comes up here is that you have to make sure that people can't collaborate with each other, because if you give two people access to the database and they have a particular privacy budget and then they combine their results, they can find out more information than they would have otherwise. Okay, and I'm going to mention this idea very quickly. Yeah, Marvin.
So to go back to the idea of the picture of the histograms, you took, it was like 10,000 drawings.
Yeah.
So that would be an example of, you know, if you only drew one point, you just have a random point on that thing, you wouldn't be able to tell very much. But if you repeat that 10,000 times, eventually the outlines appear.
Yes, exactly. So I was hoping to make that exact point. It's kind of hard to go back and forth to the slides, but yeah, as you can see on those things, if you're able to ask the same question 10,000 times, you can inform the entire distribution, and basically you get the answer. Unless epsilon is so small, you're essentially talking about the same distribution. But again, then your answers are potentially wildly off of reality. So the very last thing they talk about in the paper is something called an adaptive adversary. And to be perfectly honest, I don't get this. I read the paper, I've read other papers on the topic, I've read Dwork's book on the topic, and I don't entirely get what's happening here. But the basic idea of an adaptive adversary is that you make a query, you see what the results are, and then depending on what the results are, you take one option or the other option for successive queries, and that's why it's adaptive. And there's a bunch of literature now on how you can deal with so-called adaptive adversaries. Basically, what they show in the paper is that if the adversary has a series of queries that they can make, and then they reach a point where they can take one or the other, the way that you can achieve differential privacy on those strategies is to basically find the maximum of the sensitivity of all the functions that are applied by the adversary. And the proof is not particularly hard to follow, but even when I see the result, I'm like, okay. So I wish I could explain this better, but the basic idea is that you have an adversary which is making decisions about what to query next. And they show that you can still achieve differential privacy in that scenario. Dwork did a paper on this, I think in 2015, which is much more sophisticated and goes more deeply into this idea. And so it's kind of an active field of research, but I quite frankly don't get it yet. So, all right. I just want to wrap up, I just want to run through a couple of things that go on in the real world in this realm. There's a library that Microsoft publishes called PINK, Privacy Integrated Queries. Does anybody do .NET stuff? Okay. So Microsoft also has this thing called Link, L-I-N-Q, which is kind of like actually pretty nifty API for doing SQL-like queries from code, and PINK is sort of built on that, and so it's kind of a nice system to do real differential privacy with, if you happen to be working in that realm. Uber also has had a couple of blog posts in the last, I think, couple of years about, actually I think they're more recent than that, about an open source system that they're building to do this. And there's a paper that I list in the reference as these researchers from Berkeley wrote this paper on how to do practical differential privacy using SQL queries, which is actually pretty challenging because, again, this is kind of the adaptive situation where you could have joins in there, and so you don't even know initially how big the data sets are going to be when you start making the queries, because there could be a join, you don't know how many rows are going to be included in the new set of rows after the join happens and stuff. So they have to do some fairly sophisticated things to make differential privacy work for real SQL queries. And Uber is actually implementing a system that does this now. Apple, Google, Facebook all do this internally. I don't know if any of them have released anything to the outside world to do it, but they all do it in some way or another. Facebook does it for ad metric type data, so number of clicks, click-throughs, that type of thing. Google does it for search data. I'm not sure exactly. I guess Apple has all sorts of data they get through their mobile devices that they apply this to. And again, there was an article in Wired from, I think, just last month about how they're doing it badly and probably not accomplishing what they want to. This is kind of a picture of the system that Uber's developing. And I threw it in here mostly because I thought it was kind of interesting to show like what actually happens in a system that tries to accomplish this. So, the blue box here is basically the part that implements differential privacy. And into the left goes an actual SQL query. And this system in the blue box has access to the original database. And it it looks at the SQL query that you're making, does some analysis on it, and then adds noise to the results. And they've actually reached a point now, and I haven't seen the output, but what this system actually does is it takes a SQL query and outputs a SQL query, which is run against the database. And the new SQL query actually incorporates the noise into the SQL. And I've been doing SQL for 25 years, and I'm not quite sure how they do that, but it's a cool idea in any case. So yeah, that's pretty much it. Again, I know this is a little bit of a challenging paper, but I think it's a really cool idea, and it's a very recent thing that's still being both worked on and implemented in the real world. And so, as I said before, I think the important things to get from this are this is a randomized process. So when you make a query that's differentially private, you don't get the same results back on successive queries, and other people don't get the same results when they make the same query. The Laplacian noise is the most common way of doing ads. There's also a mechanism where people use exponential noise. And if any of you watch the videos, you probably, or videos or some of those blog posts, there's also really simple, okay, I'm going to give you the right answer this time. And you flip a coin and say, okay, on this one, I'm going to give you a wrong answer if the next coin I flip is a heads. So basically, you get the right answer 75% of the time and the wrong answer 25% of the time. So cumulatively, you get results that are close, relatively close to reality, at least enough to look at trends and stuff like that. But there's, as they say, plausible deniability in terms of any particular record. So the mechanism can be that simple. Yeah, so thank you.